3 here, we're going to talk about instantaneous rate of change of a function, instantaneous rate of a particle, which is your velocity. And so finally, the derivative of f at c is also called the instantaneous rate of change. Recall when we did AROC and IROC, we've talked about this respected to x at c. That is, the instantaneous rate of change of f with respect to x at c is denoted f prime of c. This is nothing different than what we've been doing. Okay, so now we're just putting into context of a word problem. So there's always also the instantaneous velocity of a particle at a given time x. So if we're talking about some physics, we'll talk about velocity. If something's moving, it's your instantaneous velocity. So if you're driving your car, you look down at your speedometer. What speed are you traveling? That is your instantaneous rate of change. All right. So here's our first example, example 6. The volume V of a right circular cone with a height of 6 feet is given by V of R is 1/3 pi r squared h. And since the height is 6 feet, right, this is fixed, meaning that does not change. V of R is actually equal to 2 pi r squared in this problem. That can change depending on the conditions or the parameters of different problems. So in this right circular cone, R is changing, right? So R is changing. So with that, if R is changing, the height is fixed, right? You can imagine the cone getting like thinner and thinner and thinner, but the height staying the same. We're going to find the instantaneous rate of change of the volume with respect to the radius when R equals 3, okay? So if we look at V of R, so we know V of R is equal to 2 pi r squared. We know this is because h equals 6. And we want to know, find how fast V is changing when R is 3. So basically what we're going to find here is dV dr. We're going to find this answer here. We're going to find V prime of 3. Okay. What is the derivative of the volume when R equals 3? So this becomes the limit as x approaches. I'm going to change the variable, sorry. The limits as R approaches 3. And now I can plug it into my f of x minus f of c. So we're going to have 2 pi r squared, right? This is f of x. This is V of R. Minus, when I plug in a 3, we're going to get 2 times 9. This becomes 18 pi. All over r minus 3. Okay. So again, hopefully you're starting to notice that there's always going to be some type of algebraic manipulation because I get 0 over 0 when I plug in 3. So let's see, we're going to factor, what can we factor out of here? We're going to factor out a 2 pi. So the limit as r goes to 3, if I take out a 2 pi, that will leave us with an r squared minus 9 over r minus 3. This is good. Hopefully you're seeing what's going to happen. Limits as r goes to 3, r minus 3, r plus 3, all over r minus 3. This is helpful because now we can divide those out. That becomes 1. And so the limit as r goes to 3 of 2 pi r plus 3, now I can just evaluate, plug in a 3. So 2 pi r plus 3 plus 3, so that's going to give us 12 pi. All right, so V prime of 3 is equal to 12 pi. So what this means is at r equals 3 feet, the volume is changing by 12 pi feet cubed. Right? So at that moment, that's how much the volume is changing. It's its instantaneous rate of change. Right? So again, very similar to what we did with the IROC when we did unit 6. All right. So example 7, for those of you taking physics, this will probably be very similar to your kinematics equations. Just to go back to this previous one, I forgot to mention it's changing by 12 feet per 12 feet cubed per 1 foot change in radius. All right, because we're comparing it to the radius, so that is important here, right? So dV/dr is a change in volume and a change of radius. So we're changing by 12 pi feet cubic, so 12 pi cubic feet, which is about 37.7 feet cubed per 1 foot change in radius. That is the instantaneous rate of change. All right, so going back to example 7. So for those of you that will be studying physics, this is what you've been doing, right? So this is a kinematic equation. So in physics, it's shown that the height s of a ball thrown straight up with an initial speed of 80 feet per second from a rooftop 96 feet high is given by the equation negative 16t squared plus 80t plus 96. Just note that we're in feet per second. You don't need to convert anything. This is your 1/2 AT squared. And if you're talking about feet per second, gravity's value is negative 32. So you have that taken care of there. All right, so negative 16t squared plus 80t plus 96. So where t is the elapsed time from when the ball is in the air, the ball misses the rooftop on its way down and eventually strikes the ground. See the figure below. So we're going to figure out when the ball strikes the ground. Again, you should try this independently and then see how you do on it. Okay. So for A, when does the ball strike the ground? Well, that means S of t is equal to 0. So 0 is equal to negative 16t squared plus 80t plus 96. Solve that. It is factorable. This is equal to negative 16 t minus 6 t plus 1. And so your two possible values for t are 6, where t equals negative 1. And obviously this does not make sense physically, so our answer is t equals 6. So it takes 6 seconds to strike the ball, or strike the ground. At what time t will the ball pass the rooftop on its way down? Again, you don't need to do any limits here. For part B, instead of 0, you're going to solve the equation 96, because the rooftop is 96 feet up. I'm actually just not going to go to that step. 96 is equal to negative 16t squared plus 80t plus 96. So solving this, you get 0 is equal to negative 16 t squared minus 5t. And so you'll get the answers of t equals 0, t equals 5. And so thinking about this is when you initially throw it. This is when it's going to pass by again. So t equals 5 seconds is when the ball passes by the rooftop again. All right, so now we get to what's the average speed of the ball from 0 to 2. So average speed is how the distance it traveled divided by the time. So C it's going to be s of 2 minus s of 0 over 2 minus 0. So that's equal to 196 minus 96 over 2. And your average rate of change in the first 2 seconds is 48 feet per second. Reminder that units are important here. Letter D, what's the instantaneous speed of the ball at t naught? So this is, what is the derivative of, so I'm finding s prime of t. Okay, so this is going to be the limit as h t t goes to t naught, right? Sorry, so reading the question again, sorry, I misread it. What's the instantaneous speed of the ball at time t naught? So I'm finding s prime of t naught. All right, and so if we plug that in, this is going to be given by negative 16t squared plus 80t plus 96. So this is s of t minus s of t naught, which is going to be negative 16t naught squared plus 80t naught plus 96 all over t minus t naught. All right, so now you have to algebraically manipulate that. You should see that this will cancel out with this. All right. You can factor out a negative 16. And so your result here will be negative 16 parentheses t squared minus t naught squared minus 5t plus 5t naught all over t minus t naught. All right, so this looks a little challenging, but we can figure this out. So if I look here, I'm going to group some things together. I'm going to group this together, and I'm going to group these two together. The negative 5t plus 5t naught. All right, so I'm going to group those two together. All right, so when we do this, t goes to t naught, negative 16. This is a difference of two squares. So this becomes t minus t naught, t plus t naught. Over here, I'm going to factor out a negative 5. And that's going to leave me with a t minus t naught all over t minus t naught. All right, so does everyone see what we did there? This is good because, again, I need to cancel out this t minus t naught. Okay, so now I get the limit as t goes to t naught. I can factor out a t minus t naught from both of these terms. So we'll get negative 16 t minus t naught times t plus t naught minus 5 all over t minus t naught. Now if we look here, I can cancel that with that. And so now we have the limit as t goes to t naught of negative 16 t plus t naught minus 5. And now I can evaluate my limits. So I'm going to get negative 16 2t minus 5. Okay? And so that is my instantaneous rate of change at any given time t naught. Again, algebra heavy. You have to be able to factor. You have to be able to manipulate these things to remove that discontinuity. Now we're on part E. So now that we know this, okay, so this is t naught. I can now find what. Sorry, that should be t naught. Now we're on part E. S prime of 2 is going to be negative 16 times 2 minus 5. And we get 16 feet per second. So at exactly 2 seconds, the ball is moving 16 feet per second. Letter F, when is the instantaneous speed of the ball 0? So now I can take my S prime, set it equal to 0. So 16 2t minus 5. So this means that t is going to equal 5/2, which is 2.5 seconds. So this means I reach a max at 2.5 seconds. What is the instantaneous speed of the ball? What is the instantaneous speed of the ball as it passes the rooftop on the way down? Well, we know that happens at 5 seconds. G. So S prime of 5 is equal to negative 16. 2t 2 times 5. So that's going to be 10 minus 5. So that's going to be negative 80 feet per second. And so the negative just tells us that it's moving down. Right? And so if you study physics next year or you studied this year, you understand that velocity is a vector, has magnitude and direction. And the final question is, what is the instantaneous speed of the ball when it strikes the ground? And so we know it strikes the ground at 6 seconds. We found that in part A. So part H, S prime of 6 will be equal to negative 16. 2 times 6 is 12. So 12 minus 5, and you get negative 112 feet per second is the instantaneous speed of the ball when it hits, right before it hits the ground. All right? And so that's your instantaneous speed. This is the hardest part. Okay, so this is algebra heavy. All right, and so there's your instantaneous rate of change.